All right, let's get ready for the final. This is Physics 2111. If you're not in 2111, then, well, enjoy yourself. Lecture number 1. Physics is our best model of reality. So, I'm trying to explain to you what physics is because that's what we did at the beginning of the semester. And what are we doing? We are using the scientific method. Philosophers first started doing it, and then gradually it became more scientific, and therefore we started calling it physics. And the act of movement, physical interactions. Anyway, this scientific method is where we use loops, iterations. So we go from experiment to theory and back again, right? So we go back and forth. We're going theory to experiment, back and forth and back and forth. And the whole time we're trying to get to this reality nugget that's in the middle, okay? So there's this reality that we're trying to get to. And if we work hard enough, we can approach it, right? Somewhere in there is a little point of reality. And don't worry. Even if you even if you were on top of it, you wouldn't know. Okay, so whatever. So we keep doing this, and we're always trying to get closer and closer to what reality is. And one of the examples that I like to use is we've got some theory of gravity. This is Newton's. We're getting this from Newton. Oh, gee, sorry. Pardon me. And that just basically comes from Newton's universal law of gravity, where it's, we have a little m, we have a big M, we have G over R squared in the R hat direction, and that's that. And so we get our G because mg is our force of gravity. So that's where this G comes from. And I already talked to you guys about how G is a field, so keep that in mind. It depends on where you're at, and your G will be different, right? It all depends on where you're at and what mass that is attracting you. Okay, so figure that out, and you're halfway there. Okay, so anyway, we've got things in here, though, that make this a difficult measurement, okay? So we can do all kinds of stuff. We can measure RE, but if you were to look at a planet, or the Earth for that matter, you'll have changes due to your altitude or your latitude. So if you're at the top of a mountain, up here, you're talking to the wise man at the top of the mountain, then your radius from the center of Earth is larger than it would be at sea level. The other thing is the Earth spins around on this pole, on this axis, right? And it bulges at the center. In fact, there's a mountain in the Andes that is further from the center of the Earth than Mount Everest. It's the furthest point away that's Earth, that is, ground, not gas. And because it's near the equator, and Mount Everest is a little bit north of the equator, so it's further away from the center than Mount Everest, the top of Mount Everest. Well, that's fine. If you were at the North Pole, you wouldn't be experiencing as much G either, right? Because you're closer to the center. So, RE changes, all right? And R at the pole is less than R at the center, at the equator. And R at altitude is always going to be greater than R at sea level. Okay, so these are considerations that factor in, right? And it all depends on where you're at. And even if you're at sea level, being at sea level in Norway is not the same as being at sea level in Chile. Okay, so all of that factors in. There's another thing that factors in. Even though the mass of the Earth is a pretty constant. I mean, it grows. We get asteroids and little meteors and that kind of stuff hit us a bunch. But it's still not evenly distributed. We've got sections of the Earth that are more or less dense. You can go and look at a gravitational map, and it'll say where the dense parts are and where the less dense parts are, and whole gradients of density, which means that you can make these measurements all day long, but you're still going to have issues trying to get the actual answer. So we get deviations, right, in our measurement. Now, other sciences call the deviations errors, okay? But error just means a mistake. These aren't mistakes. These are discrepancies. They're deviations. You're doing the best you can, right? Error is hard to. I mean, human error is relentless. So just forget about errors. It's always there. It's abundant. So if you do many measurements, you're going to do a whole bunch of them, and you average them all out, okay? Then that way you can get your average. You can also get your standard deviation, okay? So you get the two things. Then you can write your page, your paper, your lab report, and say, listen, I have this gravity thing for Earth, and this is what our average was, and this is what our standard deviation was. So delta G is your standard deviation, and it'll be some plus or minus whatever. And that includes all of the differences that could have been out there. All of those different ways that things could have got messed up, you're including in this standard deviation. Whoops, sorry about that. You're including in this standard deviation. So reality is out there, and we assume that there's some point out there at some point in time that there is a real G reality. And we've just got a lot of things clouding our measurement, right? There's a lot of noise in all the systems that are running out there. So all that noise makes things complicated. And so here in green, we have the real G is somewhere in this range, okay? It's somewhere in there. Otherwise, our measurements wouldn't all be in that range. So all of our measurements are in that range. So real G has to be in that range somewhere. What we do is we've come up with this, our average. So we have measured this average, and then we've done plus or minus this, okay? So we think the best chance is in blue here. Our best chance of getting G real is in the blue region. But it could be that it's not even in that region either. That's just our best chance. It could be out here somewhere, right? G could be out here. So this is reality versus what we think we're trying to do. Okay, so this is the scientific method. We'd like to think that G real is in this range of G average plus or minus. So we'd like to think this is true. And I did it again, but we'd like to think that this bit right here is true. And usually, well, I mean, look, that's a philosophical question. We kind of assume that it is, right? We assume that's true. And maybe, maybe we're wrong. I don't know. But the scientific method seems to work pretty good. So let's get into the scope of physics. So physics is universal. We talked about that. We talked about the size of the universe and the amount of time that Planck time and Planck distances, all the way up to this universal sizes and distances. And that's fine. I'm not going to ask you anything about that. But many of the aspects of nature are fractal, okay? And that includes nonlinear equations. And we're not going there, okay? So we are really keeping the class limited in a lot of different ways, okay? Ways that our theoretical equations that we chose. Okay, no, I'm not happy with what's happening right now. We chose these theoretical equations because they've been developed over time. We call them classical, okay? This is classical physics. And our class is classical mechanics, all right? So these equations, mostly from Newton, frankly, Hooke and Newton, and basically that's it. All the labs are designed to show you that the equations that we've been using in class are the same things that actually do predict reality. So hopefully when you went through and you found different ways of measuring different things, and you noticed that your percent differences were, 20% or less or whatever, then, we did a good job. We showed that those equations hold, and that was very important. So we limited, we've got limits, okay? We've got to limit our world so that classical physics will work. So we're limited in size, we're limited in our velocity, and we're limited in force, okay? The forces that we're looking at. So we're kind of going prehistoric with forces. If the object is large enough to be seen in an optical microscope, and it can't be a lot bigger than a planetary system, then that is the size that we're working with, okay? So suns, planets, planets going around suns, that kind of thing. And then, of course, any object that, if it's optical microscope, optical is the key word here, okay? Optical. That means not a laser interferometer or any of that other stuff. It's got to be, or what is it? Oh, God, FTM. It doesn't matter. Okay, so none of that, all right? So no quantum mechanics, all right, or dark matter, because that's when we start getting bigger than planetary systems. Galaxies show dark matter, dark energy, so we're not doing that. So what does that mean? That means it all centers around us. We only care about humans, basically, in this class, and that means that we're at the 2-meter scale, all right? So that's what we care about, and that's the size of which we care. All right, so next, number 2, all of our velocities have to be smaller than 10% of the speed of light. No relativity, okay? We can't have relativity. And then the third thing is we've got the force of gravity. That's our primary force. And out of all of the 4 forces, that's what we're really limiting ourselves to. But keeping that in mind, we say that we're not using electromagnetic forces. However, I told you guys, and this is true, and I need you to know this, that the normal force is basically electromagnetic forces. That's why your hand doesn't slip into the table when you put it on there, because the electrons on your hand are bouncing off the electrons on the outside of the table, and they don't want to mix or merge. Okay? The spring force is an electromagnetic force also, because the spring is bound together, and we've shaped it in a certain way, but it's bound material. Okay? So springs are an electromagnetic force as well. So, but we're just basically saying no strong force, no weak force, and we're pretending we've got blind knowledge of E&M. We're kind of pretending that electromagnetics has nothing to do with some of our observations. So that leads us to orders of magnitude and significant figures. This is it, guys. Honestly, on the test, if you're going to give me some number, I've seen it. It's 8.63957 and you won't even believe this. It just keeps going, and I put a comma there, but I don't want a comma because this is literally something that I have seen on the test written down. People write this and then they go kilograms. Holy smokes. Does anything really matter after you've rounded up to 8.64? Does any of this matter? No. I care nothing about that. Web work might, but don't do it on the final two because I will take off points. I have no problem. By now, you guys should be able to do 3 significant digits. That's these 3. Now, it doesn't mean that zeros count. Zeros do not count. So if you've got 0.02, but then there's 148 here, well, then you better write 2.15 times 10 to the minus 2. Okay? So that's that. Orders of magnitude. What's the order of magnitude that we're dealing with? That's this, 10 to the whatever. Okay, so that's our order of magnitude. So you have to have your initial digits, your 3 digits, you have to have your order of magnitude, and then you got to have your units. Okay, that is the way of the world. All right, so let's talk about the metric system a little bit. First, we've got 10 to the 0, that's just 1. Okay, everybody knows 1, that's our 2-meter scale. Everything goes off of that. Next thing you know, we've got 1,000. That's a kilometer, okay? The kilometer scale. Then we've got 10 to the 6. That's a million. That's mega. So you could have megameters. And then we have 10 to the 9. That's a billion. That's gigameters. So it all comes down to how you want to write it, okay? So you could say, the speed of light is 3.00 times 10 to the, it's 2.99, but I'm rounding up because the next thing's like an 8 or a 7 or something, to the 8 meters. So what do? We could say times 10 to the 9, and we could go 0.3 gigameters per second. Okay, we could do that. Right? So I'm substituting in the G for my 10 to the 9. All right? So, and that's C. Okay. So let's keep moving. Models, theories, and laws. All right. So back in the day, we really did believe that we could come up with things that were absolute. We thought absolute was totally in the works. Mathematicians were all about it. They were trying to prove everything, this side and that side, upside down and whatever. And they were going to prove everything and have all these laws. Okay? Laws are the things that they're like, you got to abide by the law. Everybody abides by the law. It's so, you just do it. And so laws were a thing. Well, guess what? I believe, in my way of the world, I think Kurt Gödel came out with his incompleteness theorem, and that threw everybody off track. No more laws. The laws are replaced by theories. We can get close, and it's just the scientific method. You can get close, and you have theories about all this stuff, but laws are a thing of the past. We are no longer in a place where laws are a thing. So laws are gone. They're replaced by theories, which are as good as it gets. Okay, like for instance, gravity. Gravity's real. Everybody knows about gravity. Try and escape gravity. Good luck, right? However, it's just a theory. Okay, we've got the theory of gravity. It's people who say that these are laws are they're overstating what we really can do. The same goes for evolution, by the way. Theory, okay? It's not a law, but it's as good as it gets, and it all these things work. So when it works, we teach it, okay? And that's because we can predict with it. So models are weaker than theories. And if, let's say there's some new phenomena out there that we're just now getting used to. So then we initiate models. And we go, oh, let's throw a model at this thing and see what happens. And models quickly, after a while, after enough time and effort, become theories. Okay, so that's my take on the whole thing. But the book, if you really want to get it right, read the book, and then you can tell me that I'm wrong about it, and that's fine too. But okay, so let's do some experiments. We've got physical quantities that we can measure. There are 3: length, time, and mass. These are the units: mass, seconds, length is in meters, time is in seconds, mass is in kilograms. Not grams, kilograms. Everything else is calculated from these, which, by the way, next semester, when you go to take next semester, you're going to find that they also include current in amps. Okay, so you'll have 4 things next semester. You got the length, time, mass, and then you'll have current and second semester. There are others out there that we can actually measure, but these are the basics, okay? So everything else is calculated from these in our class. So these are the examples, right? So you're just taking mass and you're multiplying it by lengths, or you're dividing by times, or whatever, and you're getting the things. And why did I write v equals xt? I should be just taken outside. Don't even. What is that? X equals vt. So v equals x over t. I can't even believe that happened. So velocity calculated. We're taking the time and we're dividing it into our length. Okay. Ugh. Jeez. All right. I don't know why I've just been off. Okay, so we use a unit system called the System International, all right, or International System, done in France, and they did great work. They've come up with all these things. These are the basic units. Everything else is done in those basic units. Okay, but every once in a while we say, well, I don't like the fact that kilogram meter per second squared is hard to write, so I'm going to call that a Newton, and now I can just write Newton from now on instead of all that other gibberish, And so a Newton is part of the System International. Okay? All right. So use your units. It helps you. You can verify what you've done. You can figure out things. I had a person ask me, theta divided by time, what is that? That's what I've got. So what is that going to be? Well, that's radians per second. What's in radians per second? Omega. These help you, okay? So use them. All right, so let's get back to discrepancy for a minute. When we're in measuring things, we've got discrepancy, we've measured a certain thing, and we want to know how far away that thing is from theoretical. So we've measured our experimental K, we've got our theoretical K, and if we write our report, we say K is equal to K experimental plus or minus our delta K. All right, that's what we've written. So what do? We want our percent discrepancy. We throw this in here. We take our theoretical K and we put it here. We get the difference. It doesn't matter. We want the absolute value of the difference because we don't care. We just want the percent difference. And then we're going to divide it by the original theoretical. That's going to give us our percent discrepancy. Okay. So a similar thing happens for the uncertainty, but this is our uncertainty in the measurement. Okay, so how much of our original experimental value is our standard deviation? If it's 90%, then wow, how well do we really know K? Not very well. So we do this. We want our uncertainty, and we just take our K, divide it into our standard deviation, delta K, and we get our percent uncertainty. Now, going back just a little bit, discrepancy is the accuracy of something, and uncertainty is the precision. Okay, how precise were you? Well, that's this. How far away were you? That's your accuracy. Okay, so keep those in mind. Scalars and vectors. We're going to do a little bit of math here. All right, scalar is just a magnitude. Vector is a magnitude and a direction. So scalars are easy. Everybody likes scalars. That's why we like adding in energy, right? Because energy is a scalar, and so we can start doing combinations of energies and subtracting energies. That's simple. A scalar and a vector can be multiplied together, and then all you're doing is you're scaling up or scaling down depending on whether alpha is greater than or less than 1, right? If alpha is greater than 1, then you're going to scale up. B is going to be larger than A. If it's less than 1, B is going to be less than A. Okay, it's easy. Scaling. That's why they call it scaling. Scalars. Two vectors can be added together. We'll do more of that later. And also multiplied together. So we're going to be doing more of that later. Symbols. I don't know why I'm throwing this in. Maybe they're on the test. Maybe they're not. I don't know. But we've got parallel, anti-parallel, and perpendicular. So it's just good to know. Keep that in your back pocket for the rest of your life. We can take a vector A and strip it down into a direction and make it a scalar. How do we do this? Well, we do A dot A. It's the dot product, by the way. That gives us A squared because this, actually, right here. A dot A is just the magnitudes of A times the cosine of the angle between them. But the cosine between A and A, that theta is 0. So the cosine is 1. So that means that if you take the square root of A squared, you've got A squared, take the square root of that sucker, and you're just basically dealing with A. All right? And of course, you're supposed to do plus or minus the square root, right? But we don't care because we're going to take the absolute value of all this stuff, all right? And it doesn't involve us. Imaginary numbers do not exist as far as we know. So, yeah, so that's our A. That's it. So another way to see that, let's just do this vector A. I'm going to take A and I'm going to dot it with A. So A dot A. And all the guys that are not I times I or J times J or K times K, that's all these guys, they're all 0, right? Because we're going to have to do this. We're going to have to do this. But if you don't have the same, they're not going to work. It's not going to work out. So this is nice. So we end up with 3 times 3 plus 4 times 4 plus 5 times 5. That gives us 50. And we can figure out what A is. It's a scalar, and it's the square root of 50. Done. So easy. Okay. Adding vectors. So I've got U and I've got V here, and I want R. I want to add the two things together. So I add them head to tail. So I put U down because I'm adding U and then I'm adding V to it. So I put U down, then I get V over here, head to tail, and then I get my R is the resultant. It's wherever V is pointing, right? That's the geometric construction of this, okay? And it's good to do. Write it on your page because it'll give you an idea of where you should end up, okay? So write it on the page. Draw a picture. It's helpful. But we really want the actual number, right? So we want to get the actual number. So we do analytical vector algebra. So we have these two things, U and V, and we're gonna add them together. What is the first thing we have to do? First, we need a coordinate system. For sure, you've got to do it, okay? So you come over here, and this is a pretty elaborate coordinate system I've drawn here, right? I've got my 0, 0 point, all that stuff, but you got to say, and it's you decide. You're the one who's going to put it on the page. You do this. That way, everybody's clear. I'm clear. You're clear. When you write your answer down with respect to whatever coordinate system you put, I have to work with that. So don't make me work hard because I don't want you to work hard. Make it simple on yourself, but don't do it on my account. I'll figure it out. Okay, so let's say that U is equal to this, and V is equal to this and this. First of all, what are the angles, right? With respect to the positive x-axis, what are those angles? Well, here's my take on that. First of all, we're going to do U. So theta U. That's the arctangent of 1.5. Why 1.5? Because this is 1.5 right there. 1.5 over minus 3. What does that give us? That gives you a negative 26.6 degrees. Now, we already know that theta U is here, and we know that it's less than 180 degrees. So why is that? Well, because it's giving us this version, okay? And so we have to take the 360 degrees, subtract 26.6 from it, and we get this. But that's pointing in the wrong direction, so we have to flip it. So we subtract again, and we get our 153 degrees. That's really theta u with respect to the x-axis. A simpler way to do it is to start with 180 degrees on the other side and go back your 26 degrees here, and that gives you your 153. But unless you draw it out, you don't know. So draw it, okay? Here's my vector. This is it. It's drawn. And I'm writing my coordinate system like this. So if I put that in my coordinate system, it's going to point over here. Now you know. Now you know that you have to do this, okay? You wouldn't have known otherwise. So draw it. Literally draw it, okay? Doesn't take that long. Okay, now theta v. Theta v is a little bit easier. Where's theta? Where's v? 3j, I'm sorry, 3i plus 1j. Okay. So that means that I'm going to take my j is 1 over 3, and I'm going to divide. So where am I at on the page here? I'm right here. And I'm going to divide 3 into 1 and do the arctangent. That's 18.4 degrees. And that's it. Why is it simple? Because we know it's in the first quadrant. We know that it's above the x-axis. 18.4 degrees is perfect, and we're done. Okay, now we want to add those two vectors together. How do we do that? Well, that's simple. We're going to take u and we're going to add v. So here's my u, and there's my v, and this is what we get when we add them together. So I've added u graphically and v graphically. I've got 0, so that means we didn't really leave the x-axis at all, and we've gone up the y dimension to 2.5, and that's my r. So r is equal to 0 plus 2.5j. What is theta r? Theta r is 90 degrees. Why is it 90 degrees? Because it is undefined at 0 in the denominator. So if it's pointing up or down, the tangent of theta is undefined, you're going to end up with a 90-degree angle. So if your x is 0 and you've got your coordinate system drawn like this, then you are going to end up with all of these, okay? And it goes on to infinity because plus or minus n pi over 2 for all n that are odd, or 1, 3, 5, blah, blah, blah. Okay? So that's it. That's just the nature of the beast. Okay. So we've looked at unit vectors and Euclidean coordinates. That's our I hat, j hat, and k hat. There are spherical coordinates. We're not going to be doing those. We haven't done them. If you did, I don't remember, and I certainly don't remember them. We did do cylindrical coordinates, okay? R hat, S hat, and theta hat. That's how I taught it to you guys. And it's a legit thing. It's fine. It's legit. It's just not how it's technically done. Okay, so cylindrical coordinates technically are r, theta, and k, or some people do r, theta, and z hat, or r, phi, and z, and they exchange theta and phi, whatever. But that's not how we've been doing it in this class. So don't confuse yourself. Just stick with these. This is a nice system to work with, okay? And our theta hat is either into the page or out of the page, the way I've drawn it here. So just stick with that. You'll be great. Okay, now once you have your R, you have either Rx in the I hat direction plus Ry in the J hat direction, probably. And you really want the magnitude, well, just like before, we did it already. You want that magnitude, you just do the dot product with itself and then take the square root. Good. That's done. You're done. That's the Pythagorean theorem. And then, of course, you can figure out your angle because you're going to do this. Ry over Rx, and that'll give it to you within the, you just take these numbers, Rx and Ry, and that gives you with respect to the x-axis. Okay? So, good. Scalars and dot products. Here's our scalars, our scalar product. You got A, you got B. You're going to multiply them together. If you have the magnitudes of those things and you know the angle between them, you can use this equation. If it's given to you like we did before, where you want to dot U with V, then here's U, there's V, you dot them together, and you get 10.5, right? Because let's do one more step here. That's 9. This right here equals 1. This right here equals 1. So 9 plus 1.5 equals 10.5. Okay? 10.5. That is a scalar. Okay? Your resultant is a scalar. That is why it's called the scalar product. We call it the dot product. Scalar means dot. You got to put a dot in between them to get your scalar product. Okay? Vector products. So we've got A cross B, same old thing. And if you do A cross B and you just want the magnitude of it, then you take the magnitude of A, the magnitude of B, and then whatever the angle is between them, you take the sine of that angle, not the cosine, the sine, all right? And that'll give you the magnitude of your thing. To get the direction, you use the right-hand rule. Okay, now do this. Do this with me. Follow along. Your fingers along the first vector, okay, A. All right, so you put your fingers along A, but you want to have it so that your palm points towards B. Okay, you have to have your palm facing to the B. If your fingers can't curl and touch the B, then it's not going to work. So if you have your hand up and you've got your palm not facing towards B, then your fingers are going to curl and it's not going to be good for it just doesn't work out. So you want your palm facing the second vector. Okay, this is the second vector. Then your thumb points in the resultant direction. So it turns out that our thumb would be pointing into the page. If we do A cross B, my thumb's pointing down. I don't know about yours. Unless you're an alien, yours is too, if you're using your right hand. So the other way of using the unit vectors, this is U cross V. So here's U, here's V. We're going to U cross V. All right? So we've got 3 times 1. Why am I doing 3 times 1 and not 3 times 3? Because if I did 3 times 3, I'd have I cross I, and that's 0. J cross J, that's 0. K cross K is 0. So none of those are worthwhile. So I'm going to do I cross J, that's this one. I've got my negative 3 times 1, I cross J. I'm going to add in my 1.5 times my 3 on the other side, and that's J cross I. And that's really all I have. I don't have anything else. Nothing else is coming about. So what happens? I cross j is k. J cross I is negative k. So I've got negative 3k plus 4.5, 1.5 times 3, negative k. All right, both of these things are negative. That leaves me with minus 7k. And if you notice, k is in the z direction. It's into the page. This is my negative k hat. Okay, it just totally worked out. Okay, everything worked out perfectly. However, if we look at our u and v, we're doing u cross v. So I have my u, I have my palm pointing towards v so my fingers can curl around and touch it, and my thumb is pointing into the page. Right hand rule works. All right, guys, we're going to stop here. We're going to do lecture number 2 in a second. As far as you're concerned, it'll be up next.